Students, in this video, we will first express CR equations in polar form. In polar form, we have, let's consider this xy plane, x and y. Suppose we have a point P here, whose coordinates are x and y. This is x, this is y. Okay. Now, we can locate the same point by a set of different coordinates. That those coordinates are called polar coordinates, and they are as this. One coordinate gives us the distance of the point from the origin. This distance is denoted by r, and the other coordinate gives us the direction in which that point is located. That is given by this angle theta. So this point has two polar coordinates, one giving it is distance directly, it is distance from the origin, and the other giving it is direction. Now the two sets of coordinates, they are related. X is equal to, as you can see from the geometry of this triangle, right angle triangle, x is equal to r cos theta, y is equal to r sin theta. These are these coordinates, I mean x and y, related to r and this, that is r sin theta, or sin theta. Now next we can go for the inverse transformation. In inverse transformation, what we do, we express r and theta in terms of x and y. R can be expressed easily. You can see it from this triangle, that is r square, or by Pythagoras theorem, r is equal to simply r x square plus y square. And then similarly, theta can be given by, instead of theta we can take tan theta is equal to y by x. Y tan theta is equal to y by x, that is theta is equal to tan inverse y by x. These are the relations between them. Keeping these relations there, we will be using them. Let us go now to expression of CR equation in the form of in terms of polar coordinates. Now we have, for that matter, consider a function, say fz. Z is a complex number, and z can be written as x plus iy. Instead of writing it as x plus iy, we can express in polar coordinates. As we have seen, z is equal to x, we have seen that is equal to r cos theta, y we have seen first I, then y is equal to r sin theta, z is equal to, taking r common, we have cos theta plus I sin theta. That gives us z is equal to r, and this is by Euler's formula. This is I e raised to I theta. This form of a complex number is called polar form. In this polar form, r is called its amplitude or modulus, and theta is called its argument. Now, in physics we call it phase. Now let us keep this thing in mind, that z can be treated as function of r and theta, just as we are treating it as function of x and y. Now one can treat it as function of r and theta. Now fz can then be written as, we have fz is equal to, we can write it now as, in place of z I can write r e raised to I theta, Now let us go to this page. Fz is equal to, that is equal to f r e raised to I theta, f r e raised to I theta. Okay. Now we know that what we do when we take a complex function, we first find it is this imaginary part and real part, because real part, as you know, we call that u, and imaginary part we call that v, and then we take their partial derivatives, things like that, and test whether the function is analytic at a point or not, analytic in a small neighborhood or not. Now In order to do the same with this, we will simply write it as u plus iv, or u plus I, where u is the real part, v is the imaginary part of this function. Now u, or I can write u plus iv is equal to f or e raised to I theta, and I can write here, I can write fz is equal to this. It has this real part u and imaginary part v. Having said that, let's now move ahead. Let's take its derivative. Say, for example, let me differentiate it with respect to, say, or. Let me first differentiate it with respect to or. Differentiating this, let me call it 1. Differentiating 1 with respect to or. I will have, and in that case, del f by del r. It is partial derivative because f depends on both r and theta. That will be equal to del u by del r plus I del v by del r, because we are differentiating with respect to r, keeping theta constants. That's why we have these partial derivatives here. And when you differentiate this with respect to r, see, first of all, treat this as the variable. This is your variable here. This term represents its variable. Your variable is r, that is here, and whole of this term is your variable. It is as if you have fx, something like that, fx, and differentiate it. When you differentiate it, you get f dash x. Instead of x, you write r e raised to I theta. Now, you don't have that simple x. You don't have something like this, fx. You have x squared, something like this. And when you write it as f dash, you differentiate it first as a whole, and then you take this, what we call a function of a function. You then differentiate this separately. When you differentiate this with respect to r, you will first get, in place of r, you will get 1, differentiating this with respect to r. And this is a constant. This will be treated as constant. So it is simply e raised to I theta. Therefore, I don't need this this first term, this side here. I will go with this del u by del r, del u by del r plus I del v by del r is equal to, I can write it f dash, I can write it as f dash or e raised to I theta into e raised to I theta. Now, equation second. Call it equation second. Next, let us differentiate first with respect to theta. Differentiating first with respect to theta. I mean differentiating first with respect to theta. If I differentiate it with respect to theta, I will have del u by del theta plus I del v by del theta is equal to, that is equal to I del v by del theta, it's not v dash, del v by del theta, that is equal to, now we have to differentiate this time we have to differentiate it with respect to theta. So r will be treated as, first let me differentiate the function as a whole, f dash or e raised to I theta, Next, I will have to differentiate this much r e raised to I theta. Now, in order to differentiate it, I will treat r constant, so r will be there. And when I differentiate this, you know that if here I had e raised to theta, I would get e raised to theta. But it has I, that I will land down, it will be I e raised to I theta. Now, equation third. My next step will be to substitute value of this quantity, f dash or e raised to I theta into e raised to I theta. Substitute value of this quantity here in this place. You know that if we separate r and I, the rest of it is the same as this, but that is equal to that is equal to this side. So this side will appear here, with r and I multiplied with this. Now we go to this, then we have to write from this du by d theta. We will start from this du by d theta, du by d theta plus I dv by d theta is equal to now let us first see this. I will first take r and I to one side. Let me keep them at the front. R I. Then I will move inside. Just 1 minute. I have taken out. Then I am left with this. I am left with this quantity. Exactly this quantity, and that is equal to this du by dr I dv by dr. Du by dr del u by del r, del u by del r plus I del v by del r. Let me check whether I am correct or not. Yes, del u by del r I dv by dr. Okay, I dv by dr. Now we multiply this del u by del theta plus I del v by del theta is equal to r. Let's take multiply this with this quantity r I del u by del x del r plus, or we can keep r there and just multiply this by this this I mean or let's keep r there, and I del u by del r plus, when I multiply this with this, it becomes I into I square, that is equal to minus 1 del v by del r. Now we can equate real and imaginary parts. If we equate this real part del u by del theta, we have for this corresponding real part on that side is this, not real part, this is real part. So it will be minus r del v by del theta, which are this or this or. Now similarly I have del v by del theta here, imaginary part, and here I have r del v u by del r. These are Cauchy-Riemann equations in polar form. You can express, of course, there are choices available with you. You can express del v by del r in terms of this. That's quite easy now. But these are the fundamental equations, CR equations in polar form. Now we have the last question of this unit, and that is we will have now to do one thing, that is to find an expression. Let us go to next page and we will find an expression for a derivative of a complex function in polar form, in polar coordinates. So the situation is like this. We want f dash z in polar form, f dash z in polar form. For that matter, we will begin with this simple equation that fz is equal to u plus iv. Okay, then naturally del f by del and here one more thing, that is this u is a function of r theta, and plus v is also function of r theta. So previously we were writing them as functions of x and y. Now we are writing them as functions of r and theta. So you have del f by del r. If we take del f by del r, that means you are differentiating this with respect to r, then you will get del u by del r plus I del v by del r, simple del r. And if I differentiate it with respect to theta, del f by del theta is equal to del f, so that is equal to del u by del theta plus I del v by del theta. Let's call this equation first, this equation second. We'll be using these two equations. Now we do one more thing, that is we know that f is function of fz is function of r and theta. So if we write it is derivative del f by del z with respect to z, We can express this total derivative by using chain rule. We can express this at del f by del or del f by del r into del r by del x plus del f by del theta by del x. Now, one important thing that I would like to explain to you is that uh, you expect there should be del z here, but I am using del x. Why? Because I am taking partial derivative of r with respect to x. When you take partial derivative of r with respect to x, then you are keeping y constant. And when y is kept constant, a change in x is the same as change in z. So this del x is as good as this dz when y is held constant. So no problem. Similarly here, when y is of course held constant, again you are holding y constant. And when y is held constant here, then you have del z. A change in z is simply due to a change in x. With this explanation, let us move forward. That is, we have what we have to do. We have to use first of all, we shall use value of dr by dx here. Or first, let me do one thing. Let me replace this here. Del f by del theta. Del f by del theta. I already had that in equation second. If I substitute it there, I get del f by del z. Del f by del z. See why I'm doing this? Because I want either. See, I have two types of these functions here. One is del f by del r, another is del f by del theta. I can express this derivative in terms of this del f by del r, or in terms of this del f by del theta. I just want one of them. So there are two expressions for del f by del z. One is in terms of theta, del f by del theta. Another is in terms of del f by del r. Both we can do both of them. I will show you one that is in terms of del f by del r. You can then use at your own level. You can use the other. How do I actually how do I express del f by del z in terms of del f by del r? I will replace this del f by del theta using this equation. But if you want to retain this here and remove this, eliminate this, then you will be using equation first in its place. That is the philosophy, nothing more than that. Del f by del z is equal to del f by del r into why I have not been talking about these two, because their values we can get easily by using relations between polar coordinates and x y. Then hence they will not remain there, they will be substituted, replaced by their values, as you will see just after one more step. Del r by del x plus del f by I'm going to replace it by I have del u by del theta plus I del v by del theta into d theta by dx, del theta by del x. Okay. Now, having written this, now I will now substitute value of del r by del x here. Equation third I will write it. Equation third, and I will have to go to next step. But before using this equation, I should first get del r by del x and del theta by del x. Del r by del x and del theta. I want this del r by del x and del theta by del x. Now I will be using this equation. X is equal to r cos theta, y is equal to r sin theta, r is equal to root of x square plus y square, and theta is equal to tan inverse y by x, tan inverse y by x. If I go to this equation first, this equation will give me del x by del r. Del x, but I want del r by del x. That is here. Del r by del x. So it is, you can, of course, one can also get del r by del x from this equation, but there is a complication. The complication is that if I differentiate this x with respect to r, now theta, I cannot retain theta as constant. I cannot say that theta is constant while differentiating this with respect to this, because theta, as you can see yourself, theta itself depends on y and x. So if x is changing, theta will be also be changing. So we will be caught in a whirlpool of these changes, x and theta. It is better to go to this. So keep this thing in mind, that this is easier for determination of this. So we simply go to and write del r by del x is equal to, it's quite easy to hold y constant here. Del r by del x in fact implies y is to be constant. So I have 1 by 2 root x square plus y square into 2 x. 2x, that is equal to 2 and 2 cancels out, x by this is r, x by r. So x by r, this is this x, this is x, this is r. Say this is x and this is r, you can see it. Now x by r is simply x by r. Now x by r, bring this r here, x by r is cos theta, simply cos theta. So this is cos theta, simple cos theta. What about this del theta by del x? Del theta by del x is, let's see what it is. Del theta by del x, yes, here is the equation where from you can get it. So it is del x by del theta by del x is simply del theta by del x. Treat y as constant, you have 1 divided by 1 plus y square by x square into derivative of this, keeping y constant. That is, if y is constant, y will remain as multiplicative constant there, and 1 by x, differentiation of 1 by x is minus 1 by x square, minus 1 by x square. So I have this situation, minus y, here I have minus y in the numerator, and in denominator I have, first multiply this, it is x square plus y square divided by x square, and here comes this x square one from this it was 1 by x square, 1 is in the numerator and x square is here, x square here. This x square goes, I have this situation, minus y by x square plus y square. The x square plus y square is r square, y by r square, which can be written as minus 1 by r into y by r, minus 1 by r into y by r, but y by r is sine theta. So I have ultimately minus 1 by r into sine theta, that is simply sine theta by r minus sine theta by r. This is the value for d theta by del x. So it is minus sine theta by r Let's go, let's move forward. We have now, let me write them somewhere. Del x del r by del x is equal to cos theta, and del r by del y, del r by del theta perhaps, del r by del theta, no sorry, it is not r, del theta by del x is equal to, it was equal to minus sine theta by r, minus sine theta by r, minus sine theta by r. Now substituting them in that equation, it was there, that equation on this page, the last equation, del f by del z is equal to del f by del r, del f by del z is equal to del f by del r, del f by, sorry, it is not partial now, df by dz, df by dz is equal to, df by dz is equal to, once again we go back, del f by del r, del f by del r, it's better to write here on some piece of paper, paper, in order to save this time. It wastes some time. Just a minute. I have this. del f by del z, del f by del z is equal to df by dz, sorry, del f by del r by del x plus del u by del theta plus I v del v I del v by del theta into d theta by del theta by del x. Now I can write it. It now becomes easier for me to write it. I have del f by del z is equal to del f by del r into del r by del x, del r by del x plus del v by del theta plus I del it was del u by del theta plus I del v by del theta into sine theta into d theta del theta by del x. Now I can substitute now these values here. Just retain this del f by del r, retain it as it is, and then write del r by del x in its place, del r by del x, that is cos theta plus now we have now del theta, del u by del theta as it is, keep them as they are. Something is going to happen to them. Let us see. Now minus sine theta by r here, del theta by del x minus that minus I will write here minus sine theta. I will write del u by del theta plus I del v by del theta and into of course into sine theta by r, okay. Now okay, it is right. Okay, now what I do is that I will use now del u by del theta plus IV del v by del theta. I have this relation somewhere. Previously we have written it somewhere. Del u by del theta plus I del v by del theta. That will be simply, you can check it there. Is equation first and second. Del u by del theta plus I del v by del theta is equal to simply del f by del theta. That is equal to del f by del theta. Now if I use this in that equation, I have now this is del u by del theta plus I del v by del theta. That will be equal to this will be equal to then del f by del theta. So I write del f by del r del f by del r del f by del r cos theta, but that will land me again in trouble. This will be del f by del theta, which I had actually replaced that. But we can also see ultimately, see there is an interesting thing, that is, let us go to this. You have del f by del, you can see del u by del u by del theta plus I del u by del theta, that is equal to basically both of them are derivatives of this. That means that you have fz is equal to u plus iv, that is equal to this, fz is equal to this, and then you have f dash z equal to, it was actually fz is equal to u plus iv. We differentiated it with respect to r. We got del f by del r is equal to del u by del r plus I del v by del r. So it is actually, I can write here, it is f del this is del f by del r. That is it. Again, it is del f by del theta. Just 1 minute. We have to have this. We have to replace this. We cannot go back to this del f by del theta. So let us go back and see where we have the problem. Now, can I replace this del u by del theta plus I del v by del theta? Can I replace this by, yes, the solution is that I have already I have established that derived rather CR equations in terms of CR equation in polar coordinates, and that was my previous question. In my previous question I had, yes, that is the solution. This is the solution. Del u by del theta is equal to minus or del v by del r. Del v by del theta is equal to or del u by del r. Let's go and write this back. Once again, I will write it here. Del u by del theta is equal to minus or del v by del r. Del v by del theta is equal to or del u by del r. Let us go back to this, and this will solve our problem, because otherwise we are landing back into del f by del theta. Now del u by del theta, according to CR equations, del u by del theta is minus or del v by del r, okay, plus I. Del v by del theta is equal to or del u by del r into sine theta by r. Thank God. That is what we actually needed. So that is equal to, this is equal to del f by del r cos theta minus now a little bit this simplification. Let's do something like this, because that will be beneficial for us. That is, if this minus 1, I can write I square for this. I square or del v by del r plus I or del u by del r into sine theta by r. Take one I common, and if I do that, if I take one I common, I get del f by del r cos theta minus. Taking one I common, I have all I am left with. And let me write this part first. This, because I has gone, now this is real part, it becomes or del u by del r minus, not minus, plus I. It is I. One I has gone out, so one I is there. One I or del v by del r into sine theta by r. Next we have to once again we have to, now we will take r common. This will be I r. Okay, we will be left with del u by del r plus I del v by del r. I del v by del r, which is exactly del f by del r. You can see for your satisfaction. You can see here. No, this is not. It is here. Del f by del r is del u by del r plus I del v by del r. Let me again write it on this paper. I have this del u by, I have del f, you see it here, del f by del r, del f by del r is equal to del u by del r plus I del v by del r. Okay, this is one. Another thing that where I am going to substitute it is here in this equation, and I have to since I have to go to next page, this equation becomes, I will write it here. You see it, del f df by dz is equal to del f by del r, del f by del r cos theta minus I. This I will replace or IR. I will write IR, and then replacing du by del r, del u by del r plus I del v by del r by df. That will be df by dr. Replacing that with df by dr into sine theta by r. Let me now go to another page. I have del f by del or del z. Sorry, it is not del. It is total derivative. Df by dz is equal to, that is equal to del f by del r cos theta minus I or or and or will cancel one. Let me first write it. I or del f by del r into sine theta by r. You can have a look at this for your satisfaction. That is del f by del r cos theta minus I. This has been replaced after taking r out. This has been replaced by del f by del r sin theta by this. So we have r and r cancels out. You take del f by del r common, del f by del r is common, then you have cos theta minus I sin theta, cos theta minus I sin theta. This is expression for derivative of a complex function in polar coordinates. So another choice is, an alternative method is to use this del f by del z. That I will leave to you. You will do it yourself. That's quite easy. The method is in as I have shown you, where you have to make a change, and at that point this will be del f by del z will be minus, it will come out to be del f by del theta, del f by del theta. Then we have there will be one more thing, that is minus I by r, which is not here, minus I by r, and you have again cos theta minus I sin theta. That is the end of CR equations in polar coordinates. Thank you.